Hey, before going back to talk about physics, Friday, this Friday I have an obligation with the college all day that hits this class, and while I originally planned on making a video for the class, it's the day before spring break, and historically the turnout is not good afternoon. So I'm just going to cancel the class. It's too much. Yeah, too much. 1,000 ways too much. Okay, so there will be no class at all on Friday. All right, so where things left off. So we're in the transition between electric power distribution and radio. So at this point, we know what's we've done so far. We've looked at electricity and magnetism separately. We're starting to see they are related to each other. We've encountered some electrical devices. One of them I'll come back to, called a capacitor, which I haven't pulled out again. But last time I talked about transformers. Transformers do the remarkable thing of moving power between two circuits by using the interactions between electric and magnetic fields. Basically, you have two circuits that are connected to coils of wire that share the same electromagnetic environment. And when you have the current in the first coil, the primary coil, varying with time, first of all, the current itself is magnetic, any current's magnetic, and if it's varying with time, the magnetic field of that current is varying with time too. So magnetic fields that change with time produce electric fields. The details of which way electric fields point, how strong they are, their shape, and their structures in space, that's complicated, and that's stuff that you deal with, physics majors and graduate students deal with, and involves vector calculus. It's a big deal. But at its simplest level, if you've got electric currents that are varying with time, they produce magnetic fields that vary with time, which in turn produce electric fields. It happens the electric fields vary with time in the case of most transformers also. So you've got electric fields around. Well, those electric fields in the transformer do two things. They add energy, they do work on charges moving in the secondary coil and send off electric power out the secondary circuit. And at the same time, they do negative work on the current in the primary coil and absorb energy from it. So energy is moving from the primary coil's current to the secondary coil's current. And this process of moving power electromagnetically from circuit to circuit is just everywhere in our electric power grid. It is the reason why our electric power grid uses alternating current. There's a disadvantage to using alternating current in that the voltage, because the voltage is going up and down, the current is going back and forth, there are moments when the electric power is zero. So the wires carrying electric power, they're not being used with perfect efficiency. If there are moments when there's no power moving through the wires, you're kind of wasting the wires. Can you do something else with them? Well, it may occur during your lifetimes that some parts of the electric power grid will convert over to direct current. The reason not to use direct current, of the sort of the type that Edison wanted to use, is it's hard to move power from circuit to circuit then. You can't use transformers directly. It would be nice, however, to be able to use the high tension wires instead of operating them where they're, again, not carrying current all the time. You use them all the time with direct current. That would be good, and it may happen because modern electronics has become so sophisticated that converting direct current to alternating current and alternating current to the direct current by way of switching systems is becoming realistic. I mean, you all have encountered devices that move power from, say, batteries. They make alternating current all by themselves. An example of this is the uninterruptible power supplies, the UPSs that many people use for their computers. Laptops have battery in them, but in fact, batteries, laptops, you're moving power from alternating current from the power company to a battery. It turns out you can do the reverse. You can move battery, which is direct current. You can move the power on. Anyway, long and short of it is, there may be moves to start using direct current for power delivery during your lifetimes. I wouldn't be surprised at all. Okay, but mainly the transformer moves power from circuit to circuit using this electromagnetic trick. Okay, any questions about that at this point? Well, there were some questions came in about inductors, and if you remember back to when I talked about just the primary coil of a transformer all by itself. The primary coil of a transformer, when the secondary coil is doing nothing, or maybe it isn't even installed, you just have a primary coil. You could say that what you've got there is an electromagnet, and it is an electromagnet. That's all it is. Run electric current in it, and you magnetize the iron in this electromagnet. It is possible to have one of these electromagnets that has no iron. It's just the current in the wires. You get a bigger bang for your buck by putting the iron in. It stores more energy when it magnetizes. So inductors that have or electromagnets that have no iron in them, it's harder to get the strength of the magnetic field, but they exist, they're important, and so that's there. But what is the characteristics of this electromagnet all by itself? It has this weird arrangement where as current flows into it for the first time, suppose there's no current, and now you turn on the current. As you turn on the current and you begin to create the magnetic field that lives inside this electromagnet, that increasing magnetic field creates an electric field. And what does the electric field do? It fights the increasing current. It pushes the increasing current backwards and tries to stop it. So it turns out it's harder than expected to turn on the current in an electromagnet. It doesn't start up very quickly. And that makes sense from a point of view of energy, is to magnetize the electromagnet, it takes energy, and it has to come from somewhere. It comes from the current, and it's extracted slowly as the current builds up its magnetic field. Let me show you this view graph while I'm talking. This guy, yeah. On the right side is one of my older drawings of an inductor. I did not put any metal inside, no steel or iron inside. So they're just four images of an inductor. The original one has no current flowing through it. It's just a coil of wire. No electric field, no magnetic field. As you start to push current through it, from the top, entering the top wire, round and round it goes, and leaving the bottom wire, which is this B picture. As you do that, weird things are happening. The magnetic field is starting to appear inside the electromagnet. And as that magnetic field gets stronger, it creates an electric field. And what does the electric field do? As I promised, it pushes the current backward, trying to stop it from increasing. So here these red loops, red arrows, are this increasing electric field trying to stop the current from increasing. Associated with this is what's called an EMF, which is associated with the voltage differences between the ends of the coil. I'm not going to pursue EMF with this story. The thing that you might remember is that this inductor fights the increase in current when you first turn it on. It makes it hard for the current to flow. Well, after a while, the current is flowing and you let it sit there for a while, and now all you've got is an old-fashioned electromagnet. It's got a magnetic field in it and around it. It can pick up paper clips and everything like that. It's an electromagnet. Life is simple. But what happens when you try to stop the current now? You try to turn down the current. Well, if you do that, the magnetic field begins to decrease, and a changing magnetic field is electric. It creates an electric field that tries to keep the current moving. So again, these electric field curves show up and push the current, trying to keep the current going. They want to they do work on the current, try to keep it going, add energy to it. So if you remember only one thing about an inductor, is it fights changes in current. If you try to increase the current going through it, it will push the current backward to try to stop it from increasing. If you try to decrease the current in an inductor, it'll push the current forward, trying to keep it going. It is a weird electromagnetic device. My first encounter with an inductor, I found it looked just like a transformer to me, except that it had only 2 wires. And I made a measurement with it. I was trying to measure it using essentially a battery across it, and my fingers, and I got the current going from the battery, and then I tried to stop the current by I unconnected from the battery while I was still holding onto the wires. And the battery slowly sent current through this big inductor, bigger than a fist. Slowly sent current through it, which I thought was very strange. The current, I was measuring the current, and I was seeing the current was rising very slowly. And then it was stopped. Then it hit a maximum and sat there. Basically, we went through this part of the story to there. And then I released the battery with my hand still attached, and it gave me a whomping shock because it tried to keep the current going. Taking the battery off was, in effect, trying to stop the current. And the inductor said, no, we're going to keep the current going, and I can be the conductor now. So I was briefly. It was a big surprise for me because I didn't know that could happen. But that was when I was a kid. Okay, so inductors fight changes in current. They're very useful in electronic devices and electrical stuff. They are around in the power grid just as inductors. The other interesting electromagnetic device that I did show you back in the early days for the class was called a capacitor. It's a big blue cylinder, the one I brought up. I charged it up with some batteries, and then I made a big spark by putting a screwdriver across it. A capacitor is just a device that stores separated charge, positive charge on one side, negative charge on the other. And with that separated charge is energy, because in effect I'm taking positive and negative and pulling them apart, an activity that requires work. And the more charge you pull apart, the more work you do. So capacitors store energy actually in the electric field between the charges. The inductor stores energy, incidentally, in the magnetic field within the current. So they're both energy storage devices. The inductor has the character that it fights changes in current. I just told you that. Capacitor has the character that it fights changes in voltage. If you have charged up the capacitor, positive on one side, negative on the other, you have created a voltage difference between, the positive side is higher voltage than the lower side. It's now hard to change that voltage without moving a lot of charge around. So capacitors are devices that tend to maintain constant voltages. Inductors are devices that tend to maintain constant currents. It's just a nice sort of symmetry in things. And they, together with just conductors, which are often given the name resistors, because they're not perfect conductors, but they follow Ohm's law. The current going through them is proportional to the voltage drop across them. Those 3 devices, capacitors, resistors, and inductors, are sort of a complete set of 3 that are used. The mathematics of them works out beautifully and is way beyond what we'll do here, but they sort of make a complete collection. You can do almost anything with those guys. And we will use inductors and capacitors in a few minutes. Okay? All right, so where are we going next? Let me show you this question. I'll actually ask it to you as a question. Oh, too many things to collect. This one. If you shake an electric charge up and down rapidly, so it's moving charge, and it's moving charge that is accelerating, because I'm going first up and then down, and then up and then down. The charges in a nearby metal object would certainly move, because if I put positive charge up here, the charges in a metal object will rearrange in response. If I move the charge down low, the charges in the middle sphere will rearrange in response also, and back and forth, okay? The question is, how far away can the metal object be and still have something happening to it, to the charge on it or in it? You okay with the question? See what you think about this one. Five, 4, 3, 2, 1. And yes, this is C. Yeah, E is a tough one, but C it is. And the point being that if you jiggle charge back and forth, which inevitably involves acceleration, the electric and magnetic results of that activity, they're not just local. They propagate, they travel forever, and they'll go clean across the universe. And if you've ever wondered, when you have a flashlight and shine it up into the night sky, does it really go forever? The answer is yes. Some of the light you've just sent off will never, ever, ever hit anything. It'll travel to the end of the universe. And the way you launch an electromagnetic wave is by taking charge and causing it to accelerate. It turns out that charge that's motionless is boring. It's got an electric field. Charge that is moving steadily is not quite as boring. It's got an electric field and a magnetic field, because moving charge is magnetic. But if you get the charge to accelerate, now it has an electric field and a magnetic field, and they're both changing in the right way that the electric field begins to make the magnetic field, and the magnetic field begins to, so the changing electric field makes the magnetic field, and the changing magnetic field creates the electric field, and they work as a team and head off across the universe. And just as, one more observation here, this is the last time I'll bring this graph up as something new, at least. And that is, we've talked about, or I've harangued about how magnetic fields can be made in a variety of ways, and electric fields can be created in a variety of ways. There's a lot of symmetry to them. The only thing not symmetric about electricity and magnetism is that we don't know of any isolated magnetic poles, no monopoles, but otherwise they're very similar. And I told you, but I don't know how to show you directly, that changing electric fields are magnetic. This is hard to demonstrate. It was hard to discover. It was, as I think I said, predicted before it was discovered, as far as I know. So the point is that a changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field, and they can work as a team, a changing electric field and a changing magnetic field, to create one another. So it's kind of like there's a famous Escher drawing of a hand drawing itself. It's basically doing that. And let me give you one version of the structure of an electromagnetic wave. If you move charge around locally, up and down, back and forth, and again, it's got to be accelerating, it will have local effects. It will push charge, and it will, around near it, it will attract magnets and turn compass needles near it. And so some of the activity is local. But part of it will head off across space, and it can go forever. It may not, because it may interact with things that ultimately absorb it, for example, or reflect it. But that traveling wave, it's called, has a particular class of structures. There are rules governing what the wave looks like. And let's take a look. I'm going to show you here with this static, old-fashioned drawing of the wave, and then I'll go play with my videos, my animations they're part of the book, and I'll show them to you and try to make sure you got an idea of how they work. This picture here is essentially a flash photograph of an electromagnetic wave moving to our right, and it's at one moment in time. And what do you see here? Well, first off, there are no charges around and no magnetic poles around. It's just an electric field and a magnetic field all by themselves. And the electric field happens to be vertical. And what's going on there? That means as you go, we're actually examining the wave on this horizontal axis. The wave is not waving up and down like a water wave, where it's actually going up and going down. It's pointing up and pointing down. We're along that axis itself. And so at this very location, right there, the wave consists of an electric field pointing upward and quite strong, as represented by that arrow. I think there's over the years, I've changed this drawing in various ways. I think the latest version of this drawing that's around in my collection of drawings has the arrow balanced so that part of it is below the axis. The point I want to convey to you again is the wave is not leaping up and down like the wave on an ocean. It's just traveling straight across, and it's merely pointing up here and pointing down there, pointing up. And it's pointing up and down electrically. So if we come into the real world here, and I'll animate it for you with my hands, we're watching the wave along this axis, heading to your right, at one moment in time. So we freeze it, okay? And we look right here, the wave is pushing up. And how we do that, how we tell that? Put a charge there and watch. The charge will accelerate upward. It's being pushed, okay? If we come over a certain distance and put the charge there and watch, it's pushed down. So that's what we're seeing here. This wave has a structure to it along the horizontal expanse, where in some regions the electric field pushes charge upward, and some regions the electric field points downward and pushes charge downward, okay? The electric field by itself isn't enough, though. The electric field is there, but something has to create it. There's no charge around, so something's got to make it. What's making it? A changing magnetic field. There is also a magnetic field present. Again, in this freeze photograph, you can't see that anything's changing with time. So I got to bring in time in a minute, and I'll do that with an animation. But there is a magnetic field present at the same location in space as there is electric field, and that magnetic field in this case is horizontal. It points alternately toward you and away from you, toward you and away from you, depending on where we are along the left to right axis. And those two fields, the magnetic field that's vertical, pointing up and down alternately with location, and the magnetic field that's pointing alternately toward you and away from you with location, those two are changing with time, and they are creating each other. And they will keep doing it all day. And as they do that creation, the crests and troughs of this wave will move. They can't recreate each other at the same location, because then nothing's changing. So they do change, and the ripples across, it moves. It actually moves very fast. It moves at the famous so-called speed of light. A bit about speed of light. The speed of light is a very special speed in our universe. It has nothing to do really with light. It's the top speed. It's the speed dictated by the nature of the relationship between space and time, a la Einstein and the theory of relativity. It happens that light travels at that speed. Other things travel at that speed as well, but light has to travel at that speed. You can't go faster than that speed. So some people talk about what would it be like if you travel faster than speed of light. Well, you can't. The nature of space-time makes it not work right. So this pattern will move with time. It will move very fast. And if you watch as it goes by, you'll see the ripples come by. For example, at this moment in time, right here, the electric field's up. If we let a little bit of time go by, not much, one of the troughs will come in, and we'll have electric field down. And a little bit of time later, we'll have electric field up, and so on. And the electric and magnetic fields move together. That whole pattern shifts together. This arrangement, incidentally, where the electric field is vertical and the magnetic field is horizontal, is known as vertically polarized, a vertically polarized electromagnetic wave. We'll see down the road, it's also known, if it were a wave of the right character to be visible light to us, because that's what light is. Light is these electromagnetic waves. So right now I'm talking about radio waves. We'll get to the distinction between radio waves and light, which is just a matter of distances and size. If it were light, we'd call it vertically polarized light. And this matters because how you perceive the world, when you look out and watch light come at you, you see aspects of the world that preferentially choose one polarization over the other. I don't want to get too far ahead of us, but for example, if you wear polarizing sunglasses, they are selecting out a certain type of polarization in the light. They happen to allow you to look at vertically polarized light especially well. They selectively kill off the other choice, which is horizontally polarized light. I don't want to make too much of that yet. But basic idea is electric fields is pointing up and down and up and down and up and down. It's not pointing toward you or away from you at any moment ever in this particular wave. The other wave that I've drawn here is what's called a horizontally polarized electromagnetic wave. It's just the top one rotated 90 degrees around us, like a rotisserie axis. It's rotated toward you. Same idea, the electric field now is alternately pointing toward you, away from you, toward you, away from you, across space, and with it the magnetic field's up and down and up and down. Okay? So let me see whether I can play the video. I want to play you a video of a vertically polarized electromagnetic wave. Here it goes. So there goes the wave along, and now we allow time to go by. And can I get this guy to loop? How do I make it loop? Play, edit, repeat. Ooh, there we go. Okay. With a little luck, it'll keep going. And it does. All right, yay. So you can see the wave is actually moving to the right. You see, pick any structure you like and watch it. It's going to the right. As I claim, it goes to the right at the speed of light. And this is in the absence of anything. This is empty space. We even took the air out just to make it really empty. There goes the wave. You can see at any given location, the electric field is varying up and down, and it's a changing electric field, so it creates a magnetic field. And sure enough, there's a magnetic field at that same location in space. And it's varying from away from us to toward us, to away from us to toward us. And since it's a changing magnetic field, it creates an electric field, which is the original electric field. They're creating each other back and forth and back and forth. It's kind of an amazing interplay between those two fields, and they travel forever. So far, so good? A few characteristics of this, so I can start talking about them nicely. There is what's known as a wave. This is one particular wave. There are lots of choices. We can play with the polarization. I've got an animation of horizontally polarized wave, but just the colors change. It's a little more than that, but yeah, it rotates. It's rotated toward us. What I want to point out, though, is this particular wave has what's called a wavelength, which is the distance between any feature and its corresponding feature the next cycle over. So for example, if I look at this peak right there, there it goes, this far over is that same equivalent peak. They're separated by about half a screen. So the wavelength of this wave is from there to there, there to there. On the screen, it's just like 2.5 meters or something like that. So that's called the wavelength. It's very similar to the wavelength of a water wave. So I said, don't think of this as a water wave, but waves are waves. There are a lot of corresponding features in them. And water waves have wavelengths too, which is the distance between crest and crest, or trough and trough. You okay with that? Radio waves have long wavelengths. That's why I start with them. Long wavelengths meaning the radio waves that most of us care about are bigger than the distance between my hands right now. So the crest and the crest. It turns out that some of the AM broadcasts that you may still listen to have waves that are hundreds of feet, even hundreds of meters from crest to crest. They're really big. We will work our way from those through microwaves, which are getting to be less than a meter between crests. And your cell phones are using microwaves, really. They're working with stuff in this range, crest to crest. If we get closer and closer and closer, little, teeny little wavelengths, you get light. You go even shorter, you get beyond light into X-rays and stuff. But they're all related. It's just a matter of how far apart the wavelengths are. Another feature worth knowing and paying attention to is what's known as frequency. And frequency is how many crests go by you per second. So we sit at one stop point and we watch the crest go by. There goes a crest. Now we're seeing a trough. Here comes a crest, at least the electric field. Crest. It's coming along again. Crest. How many crests go by per second? It might be 100, it might be 1,000,000, it might be 10 to the 15th crests go by. That's the frequency of the wave. How many cycles pass one point in space per second? All right? Let me stop this guy. And so where is this going to connect us with radio? Well, I told you that the accelerating electric charge will have local effects which are interesting but unimportant for radio. But they also have these effects that head off across space. So some fraction of the electric and magnetic field that you create by shaking charge travels on into the self-perpetuating structures that head off. So how do you actually launch those waves effectively? Just taking a small amount of charge, like a battery. In principle, if I take a 9-volt battery and go back and forth like this, I am actually launching electromagnetic waves, and off they go, and it's not a very effective way of doing it. It's real. I really did launch waves. They really did head off. Some of them probably got absorbed by the room, but probably some of them went off and escaped from the Earth, headed off, and they're going to travel forever. But it's kind of a silly way to do it. How can we do better? And the way we can do better is by moving large amounts of charge rhythmically up and down on a wire, an antenna. It is also possible to launch electromagnetic waves by jiggling magnetic pole up and down, but since there's you can't make a current of magnetic pole because you don't have anything to work with, no magnetic monopoles to push around. So it's hard to launch electromagnetic waves magnetically. It is done, but it's for the experts. Okay, so mostly it's done by jiggling charge up and down. And when you do that, if you jiggle a charge up and down rhythmically, and you choose a particular frequency for the jiggling motion, the wave goes out with a particular frequency as well. And I just told you what frequency is. It turns out that frequency and wavelength are inherently coupled. You can't change one without changing the other because the speed of the wave is fixed and they are related to each other. And I'm not going to do that right now. Just point out that if you jiggle a charge rhythmically at a certain frequency, it's going to launch a wave with that same frequency. And somebody far away, looking at the passing electric and magnetic fields, would notice various stuff coming in from various directions. The waves from that radio station, the waves from this person's electric mower not working very well and having electrical disturbances. And they'll also see the wave coming from that original transmission. To receive that wave, and to really to identify it in the midst of all the other soup of waves that are going by, because the world, the universe are full of electromagnetic waves. It's very easy to launch them, and so they're all over the place. So if you want to see that one, you know what frequency it's at. So you want to be selective with somehow your gadgetry is designed to identify that frequency of wave and maybe a little bit that direction of travel so that you get the wave and ignore everything else. And so how in the world is all that done? And one of the classic approaches, it's not quite so mainstream anymore. It used to be just absolutely essential, but it's with modern electronics, you can do things that were previously just impossible. If you want to get the charge, if you want to launch a wave with a well-defined frequency, so the crests are beautifully spaced, they have a fixed wavelength, they have a fixed frequency, you watch the electric fields go by, for example. You do it with a system that moves charge rhythmically. What's called then an oscillator, or oscillation, vibration, they're really very similar terms. Vibration usually we think of in terms of something moving physically and maybe making sound. Oscillations may be more general, but the point is being we're going to take an antenna, a piece of wire, and we're going to rhythmically move charge up and down on it. And ideally, we would get the charge moving a little at a time so that we don't have to keep shoving the charge up and then shoving it down and shoving it. We want something that has a natural rhythm to it. And so let me briefly introduce, for this semester, the idea of an oscillator in general and a harmonic oscillator in particular. This is an oscillator. It actually is also harmonic, but let me do it. It's an oscillator meaning that it can handle energy, it's a little bit of an aside, energy in two forms: kinetic energy, when it's moving, and potential energy, specifically gravitational potential energy, when it's at the ends of its swing and has actually risen up higher. If I swing it, it goes from this height to this height, so it goes up higher, right? So if I get this guy going, it's now an oscillator. It's taking its energy from one form to the other. Right now it's gravitational potential, kinetic, gravitational potential, kinetic, gravitational potential, kinetic, back and forth. These are very common, this kind of thing. The world's full of oscillators of this sort. You can also think of this as a battle between inertia, where the object wants to keep going straight, and some kind of force that is designed to push it back to a specific location. In this case, there. So the two are playing off on each other. Now, this particular oscillator system is a harmonic oscillator. And what a harmonic oscillator means is that, first off, it has a place, a situation which is at equilibrium. It loves this spot. I can put it here, at which point it experiences zero net force. It will sit here all day. So it's got a equilibrium. It also, that equilibrium is stable in the sense that if I disturb the oscillator from equilibrium, influences, whether they're forces, torques, doesn't matter, they arise that push it back towards equilibrium. So this is stable. It's stable the way a tricycle, for those who took 1050, it's stable the way a tricycle is stable at rest, or a four-legged chair is stable at rest. If you tip it, it goes back. All right? And last but not least, the influences that show up when you take it away from equilibrium are proportional to how far you take it away from equilibrium. So if I take it a little away from equilibrium, it gets little forces back. If I take it a long way from equilibrium, it gets big forces back. Okay? So that's a harmonic oscillator. What are the features of a harmonic oscillator? One important one. It goes through its motion with a certain rhythm, meaning a certain frequency, for example. This guy's got a very low frequency. It takes 4.5 seconds to complete a full swing back and forth. So its frequency is about 0.2 cycles per second. It's really slow, okay? But it does that. This kind of oscillator has a frequency that doesn't depend on how far it's swinging. This is a little swing, 4.5 seconds to complete a cycle. What's called its period is 4.5 seconds. If I make it do a bigger cycle, and try not to knock anything over, but still 4.5 seconds. It doesn't care. Oscillators of this type that have a rhythm that's independent of how big the motion is are all over the place too, and they're really important in everyday life. All the musical instruments, with rare exception, are these harmonic oscillators. Instruments that make the same pitch whether you play them loud or soft, is really helpful. If you had to play, if playing the piano, you had to change key, which key you pressed if you wanted to play loud middle C, would be a nuisance. So harmonic oscillator, most musical instruments are based on harmonic oscillators. They have a rhythm that doesn't depend on how big, on loudness, for example, or how big the motion is. Okay? So harmonic oscillators. Any questions about harmonic oscillators? All right, so there's an electromagnetic harmonic oscillator that's very common and important. And that electromagnetic harmonic oscillator has a name. It's called a tank circuit. Here's a non-moving demonstration of a tank circuit. Tank circuit consists of only two parts: a capacitor and an inductor. There's the inductor, coil of wire. Familiar, right? I told you about capacitor. I reminded you we actually encountered it early in the semester, and I haven't brought it up again until today. But capacitors like to keep voltage constant. Inductors like to keep current constant, and they make a great team when you wire them together. And when you wire them together, you can get this oscillating behavior where energy moves from one of the objects to the other, back and forth rhythmically. And let's watch it for a moment. In this image here, the capacitor is charged, meaning it's got positive charge on one of its surfaces, negative charge on its other surface. There's energy stored in its electric field. So all the energy is in the capacitor right now. And because of how this thing's arranged, of course, if you've got this is a high voltage, large positive voltage on this top plate, and large negative voltage on the bottom plate. Well, you've got a wire here. That wire can allow the charge to opposite charges to get together. So they do. So they try. They begin to move, and they go through that coil of wire. And remember, the coil of wire, because it has the characteristics of an inductor, it doesn't allow the current to just immediately flow like crazy. It doesn't like changes in current. It fights them electromagnetically. So the current builds up slowly in the inductor as the inductor's magnetic field builds up. So as current is flowing, as the positive charges that used to be on the capacitor are getting together with the negative charges that used to be on the capacitor, the current is increasing in the inductor until finally the inductor is chock full of magnetic field energy, and there's nothing left in the capacitor. It's uncharged. So all the energy moved. And it moves back. It recharges the capacitor. The inductor doesn't like to have the current stop. So once all the energy is in the inductor, and the current, it might seem like there's no point in current ever flowing again. No, the inductor says, I want to keep that current going, so it fights to keep the current going, and it ultimately recharges the capacitor. So, and it does the same process upside down over and over again, and I can show you this with an animation as well. Where's my tank circuit animation? Here it is. Rate this app. Oh yeah, I'm going to do that. How many surveys do they ask? Don't trust any survey that says we'll enter you in a lottery to win some great, wonderful thing if you complete our survey. They're then getting data selectively from people who believe they're going to win the lottery. And sorry. It drives me nuts. Okay, as you can tell, so this is a tank circuit with the energy sloshing back and forth. The energy is currently all magnetic right now, and now it's going to be all electric, and now it's all magnetic, now it's all electric. I know there's a lot of action going on here, but basically, it's got this rhythm to it. It is a harmonic oscillator. It fits the bill. Whether you have a little energy sloshing back and forth or a lot, the rhythm is the same. It depends on the nature of the coil and the nature of the physical capacitor. Nice rhythm. And having shown you this, getting all the details right in this animation was a lot of work. But do I care whether you remember them all? No. What I do want to show you is, well, actually, that thing over there on the right that you've been watching, maybe wondering what the heck it is. It's a tank circuit. That's what we got here. There's the capacitor. There's the inductor. They're wired together as a pair. There's actually a light bulb in there too, making life a little different. But this has a natural rhythm. And instead of starting it with energy in it, I'm going to try to put energy in rhythmically with a, here's what we're going to do. Just as this ball has a natural rhythm, I can put energy into it by giving it one giant shove, of course, or I can push it rhythmically and build up the energy. Now, if I pick the right rhythm to push it, so I'm always doing work on it, I build up the energy bit by bit until there's a lot of energy in it. I'm getting it going by, this is how you push a kid on a swing. You push him in sync. If you're not watching and you just push whenever, it's not going to be very effective, right? So you can't just push it whenever you like. You got to push it in rhythm with its natural frequency. Note to self, that demonstration is actually potentially dangerous if you hit it out of cycle. All right, so what I'm going to do is I'm going to electrically nudge this tank circuit rhythmically. We're actually doing it right now, and it's responding a little bit, but it's being nudged at the wrong frequency. So let me try getting the right frequency. Here we go. I'm going to nudge it at better and better. I'm going faster and faster, which is what it likes. We're now there. That's its favorite right there. That's as big as I get. The green, as big as I get. If I go higher frequency, I'm hitting it too often. It likes this. Here's slower. There's its favorite. There's faster. That's the resonance. Now, the word resonance shows up in your world. It's associated with these oscillators, and when you match the natural frequency of the oscillator, you are in resonance with it, if you want to give that sort of jargon. Actually, the light bulb is now lit because of the character of this particular circuit. If I go off resonance, the light bulb goes out. This is resonance. That's off. That's high frequency off. That's resonance. That's low frequency off. Anyway, the detail doesn't matter. But, so where is this in the world of radio? If you take a tank circuit and you give it the gentle nudges you use electronics to give it gentle nudges, you can build up a lot of energy going back and forth.
Metal detector?
Metal detector?
Yeah, you want to show them how it works?
Okay. So Al says this is how you can detect metal. Okay? He's going to mess up the resonance probably.
So you put the stick?
Yeah. The inductor, you're changing, you operate it on resonance. He's operating on resonance. It's got a favorite frequency. You're whistling at it at its favorite frequency. It's going crazy. It's happy as a clam. But when Al stuck the steel into the inductor, he's changing it's a different electromagnet.
It's a different induction.
Yeah. So he's spoiling the resonance. He's shifting the resonance. We could find it again. Yeah. But you can see, so this is a lot of metal detectors operate this way. They have a tank circuit in effect, like that, the coil that people are there at the beach sweeping around with. It's a tank circuit, and it's on resonance. Or for example, it was on resonance. And if they go by metal, the resonance changes, and they're no longer on resonance, and they detect that shift. Okay, but let me just give you the last detail about an antenna. And I can show you one last video here. Tank circuits have a rhythm they like, and you can give gentle pushes electrically to get lots of charge moving back and forth in the tank circuit, lots of energy going back and forth in the tank circuit. And if you arrange the tank circuit, shape it correctly, you have charge accelerating like crazy. It can launch a very strong wave. And let me show you this image. And what this is an image of is charge sloshing on a very strange looking tank circuit. It's a tank circuit that has been yanked. Not that way. No. Come back here. I want to make a loop. There. Okay. Remember, the tank circuit had a capacitor on one side and an inductor on the other. What if you grab the two plates of the capacitor and you yank them apart and you pull the coil of wire straight and you squeeze the plates down until they're just nothing much? It's still a tank circuit. It's still got a capacitor at its ends and a not very coily coil of wire at the middle. It's an antenna. So that's what this is. This vertical wire is still a tank circuit. It still has a natural rhythm. It happens to be a very fast natural rhythm, necessarily. But you can get charge sloshing back and forth, and the energy goes from electric field to magnetic field to electric field to magnetic field. So that's what's happening on antennas. And these are very good at launching those waves that travel across the universe, electric and magnetic fields as a team, whizzing off. There's a vertical electric field, which is good for a vertical polarized wave, and a horizontal magnetic field, which is good for the vertical polarized wave. And they work as a team, and part of the energy in that sloshing motion leaves, departs as a radio wave, and off it goes forever. All right. So have a great spring break, and we'll resume on the Monday after.